All right, good morning. Okay, let's get started. So, first thing, are there any questions that we have on anything before we get started? Everybody's good? Quiz 1 coming up this coming Tuesday. I will post some practice quizzes because some of you are learning, and this is not just you, it's statistics students in general. You know, understanding populations, variables, parameters, it takes a little bit of work. So I'll put up 2 practice quizzes by Friday. I have them written and I'm gonna run them past the SI Greg. And hopefully by then we'll get some feedback and I'll post them for Friday. So how many people went to the SI session? Can I just see a show of hands? Okay. How did it go?
Well, like the activity 2 was kind of confusing and very tough.
Good. And it's supposed to be. I mean, the confusion's intentional. It's to make you think. The way that you very often do it in stats class is you just kind of fill in the blanks. Like, what does the teacher want? Oh, I know it's this. But in real life problems, there's no one there to tell you what to fill in the blanks, right? Okay, so what I'm going to do today, I'm going to do 2 things. I'm actually going to make a recording of today's class because a couple of people are going to be out for various reasons. So if you're on sports teams or whatever, let me know ahead of time. I'll try to make a video. I can't do it for all class lectures just because not all classes kind of lend themselves to that, but I'll do my best. So your voice is being audio recorded. So if you're in the witness, protection program or something, just, And what I'm going to do is I'm going to start off with the handouts from chapter 3. So you can go ahead and download that if you haven't yet. And this kind of functions like an overhead, so I can write on it, and hopefully my handwriting won't be too bad. Okay. There we go. Okay, so we're looking at chapter 3 now, which is about taking samples. So where are we at? Okay, so right now we've talked about how we have to form a statistical question, right? This is chapter 2. And we said statistical questions are always questions about what? This you have to know. A statistical question is a question specifically about population. More specific. You're right, it's about a population, but a little more specific. The value of a parameter. That's a very fundamental fact that you'll have to know in this class. So these questions are always questions about parameters. And what is a parameter? Well, a parameter is something that summarizes all the values for a variable in a population. But there's a problem with that. We can't get the population. So the population, just to kind of review, because this is a question that comes up a lot. So how do we define a population? Michael, how do we define population? I'm sorry? Okay, that's pretty close, yeah. No. So why is that answer wrong? It's a good response, but why is that not quite right? The things we're getting data from, why is that not quite right? Yeah. So it's all the things that we want to get the data from. Okay, is all of the things that we would need to know the information from to answer our question, right? But like the old Rolling Stones song says, you can't always get what you want. Populations tend to be very big. And even when they're not big, it tends to be very cumbersome and very expensive to get all of the data. Okay, so we have it in our mind that there's some big group of all the things we're interested in. That's our population. Now, one thing to bear in mind, I had a student, he was actually a graduate student here. He was a fighter pilot, and he was doing his thesis on F-16s. And F-16s are really popular planes, right? But the problem is they're getting old, so the military has to modify them. And he wanted to look at how the modifications were affecting the accident rate, okay? Or if there was a relationship. And he said to me something really interesting. He said, the Army gave me, or the Air Force, sorry, gave him all of the data on the F-16. Now, did he have a sample or a population? Very tempting to say that. So here's why it's not a population. And it's very tempting, and that was his question. It's a very good question. It isn't a population. But the population goes to the motivation. Remember, the population really comes from the question why. So why do you want to use this data? He wants to use it in the future, right? In order to use it in the future, you would have to know about all flights under all conditions with all different types of pilots, right? So very often, even when you have what looks like a population, it's just a snapshot in time. If you're going to use it in the future to make predictions, there's going to be things in the future that aren't like the data that you're actually looking for. So it can be very tricky sometimes. You'll go off the internet and you'll download, all the data, and you think I have a population. You have to think carefully. Do I really have a population? So populations are sometimes impossible. Sometimes very difficult to get. And of course, I have to know the variable, right? And if I have a quantitative variable, the parameter I'm interested in is pi. I'm sorry, mu. So I'm going to have some question here about the population mean. If I have a categorical, it's pi. I'm going to have some question about the population proportion. What percentage of people are going to vote for a certain candidate, right? Everyone in the population. So what is the solution to this? Can't get everyone in the population and give up and go home? No. We do the reasonable thing. We take a little chunk of the sample, right? A little chunk of the population. That's our sample. So our solution is here to take a sample. And so one thing we're going to use very rarely is we're going to use capital N for the population size. And the number of things in the sample we call the sample size. So N is equal to the sample size. And it's equal to the number of individuals in our sample. So our sample is just like a little chunk of the population. Okay. And what do you think we're going to do with that data? Yeah, Bill. Okay, so N is equal to the sample size, and that's just equal to the number of individuals in the sample. Okay. So what do you think we're going to do with the data from the sample? We want to compute the parameter from the population, right? The parameter is the one value we compute. We can have all the data values in the whole population. We have a sample, so what does it make sense to compute? The same thing, except for the sample, right? So this is the idea. So we're going to compute the same quantity we want from the population. It's just going to be from the sample right now. So what we're going to do is we're going to go ahead, we're going to collect data on our variable of interest. And we're going to compute the same thing we would have computed for the population, but just for the sample now, right? So in other words, if we kind of go down to this table here, right? If we have a categorical variable, what would our population parameter be? Population percentage or proportion, right? Be pi. Our population proportion or percentage. So this is what we do in political polls, right? What percentage of people are going to vote for Trump? Well, it's impossible. There's 150 million registered voters roughly in the US, right? Absolutely impossible to get responses from all those people. So what do the pollsters do? What does the news agency do? They take a small group of people, about usually under 3,000, right? Call them up, random digit dialing, phone surveys, ask them, are you going to do this? Are you going to support this person or whatever? And what do they compute? The sample percentage, right? So here they're going to compute the sample percentage. So anyone know from the reading what the notation for the sample percentage is? Sample proportion? Pi hat. That's actually a hat. So it's called a circumflex, but we'll just call it a hat, okay? So that's what we would do. If we wanted to know the population percentage, generally wouldn't be able to get it. Take a small chunk of that population, that would be our sample, right? With the values of the categorical variable in that sample, we compute the sample percentage. And again, it kind of goes back to what I said in the beginning. Statistics is really common sense, right? That's what a reasonable person would do, okay? What if we have a quantitative variable? What's going to be our parameter here? Mu, right? The population mean. Again, generally can't get population, so we're going to take that sample instead and compute the average for the sample. So we're going to compute the sample average for the sample mean. And I'm going to write this as mu hat. It's like a little pointy hat. Yeah. Okay. And so I'm going to use percentage and proportion with equal frequency. They're equally used. Again, mean and average, I'm going to use it with equal frequency. Okay. They're interchangeable. Okay. A few things to notice. So one of the things I'm going to be really picky about is when you're saying, oh, the mean is this. It makes a difference which mean you're talking about, right? We have two means. We have one from the population, the thing we're trying to find out about, then we have another from the sample. The thing I really want to impress upon you is how different these are, okay? So first of all, you should realize that population parameter, you have this, what's that called in English? Alliteration? When they start with the same letter, something like that? Okay, thanks. So population parameter, sample statistic. You should know the definition for statistic. I could put that on a quiz, actually. It's a very basic term. You can't graduate a course in statistics and not know what a statistic is, right? Okay. So this is what we want, right? We want the population. We can't get it. This is what we actually get, okay? The population parameter is a fixed number. In other words, the percentage of people that are going to vote for Trump right this minute, if I was an omniscient being, is an actual number, right? Now, if you look at the sample statistic, is the sample statistic fixed? If I draw, say, 1,500 people, and I ask what percentage of people are going to vote for a certain candidate, then I put them back in the poll, put them back in the registered voters, shuffle them all up, and pick another 1,500. Am I going to get the same percentage each time? No. The sample statistic is actually a variable. It varies from sample to sample. And that's a very important point that we're going to use a lot, okay? So this is actually variable. It's fixed for a certain sample, but from sample to sample, it's going to vary. If it didn't, we wouldn't have any statistics, right? It'd be very boring. Population parameter unknown, sample statistic is known if you have the data. So again, to emphasize why it's so important to make the distinction between those two, because even though they're very similar in some senses, they're also very different in some senses too. Okay? Now, we talked before how to remember parameter, right? So we said the reason why we use the Greek letter is because it's all Greek to us. In other words, we don't know the population parameter. And that's what all Greek to you means. And the way we remember the sample statistic with the hat, the way I was taught is, if it has a hat, there's a person under it. Okay? In other words, it comes from a sample. Okay? So if there's a hat on it, there's a person under it. In other words, it comes from an actual sample. Okay? This came from actual individuals. Okay. So any questions on notation or kind of the ideas here that we're doing? Everyone's good? Okay. Now, this is the idea of what's going on. And it's very tempting to kind of look at this in a simple-minded way. So what I'm going to do is I'm going to go back to this example. This is kind of a little cartoon of the Planet the Land fitness problem we were talking about. So we were talking about how fitness clubs want to have more than 50% female. The land wanted to check and see if they were meeting that goal, right? And so, maybe here's all the Planet Fitness members. I think actually this was a CEO, because this is all new Planet Fitness members, right? So Planet Fitness in general, all Planet Fitnesses wanted to know if they were meeting that goal. So the population, the things that I want to get data from, are all the new Planet Fitness members that year. I could do it, but it's hard. You'd have to contact every single person, get the data, wait, and you have no idea how screwed up data you can get, right? So you could do this, but it'd be very expensive to do. So the smarter thing to do is just get a sample to estimate the parameters. So in this case, if we thought that the land was kind of like what an ordinary Planet Fitness was, we could use that as our sample. And so from all the people in our sample, from just the land Planet Fitness, we compute the sample percentage. We want to know about the population percentage of females. That's too hard to get, too expensive to get, so we're going to get the sample percentage. Now, what do we conclude from the 52%? Remember what the question was? Is pi greater than 50%? What would we conclude? But I'm not interested in the land Planet Fitness, am I? That pi is standing for all Planet Fitnesses. What can I say about that pi? What can I say about the population percentage of the females in all the Planet Fitnesses? So here's the problem. And this is a hard question. This is like chapters down the road. But can I conclude from this that the population percentage is not 52%? Polls can be wrong. Surveys can be wrong. Samples can be wrong. The election was a great example, right? People took samples, computed percentages, and guess what? Those percentages do not correspond to the actual population percentage, right? In the 2016 election. So we don't know. This pi hat is a variable. It's going to vary from sample to sample. Maybe we just happen to get a club where they're a little on the high side. Maybe the real average would say 48%, right? We don't know right now. We will by the end of the class. So here's kind of the point. It's on the one hand, we want to estimate the population percentage. So samples estimate populations, right? That makes sense, okay? I want to know what percentage of people in the population are going to vote for a candidate. I get a sample, I compute the sample percentage. That should be an estimate. An estimate means it should be close. If you go to the mechanic, it's kind of like an estimate for a car repair. If you go to a mechanic and you say how much for a brake job, and he says $350, and you come back and it's $780, that wasn't really an estimate, was it? If it's $380, $310, it's in that ballpark. So we want this to be close, okay? So the one purpose of these statistics are that they're going to estimate the parameter. But the big thing, and this is the hard thing, is we want to make a generalization about this population proportion from this sample proportion. Now that may not seem like a big deal to you, but that is a huge leap. Let me just give you an example. So if you go back to the registered voters, right? The population size for the registered voters is 150 million people. This is the number of registered voters in the US. Roughly, give or take, 1,000 or something, okay? So this is all the people that I would have to get the data from to know conclusively what the population percentage is in some sort of presidential election, right? The sample sizes, on the other hand, are incredibly small. They're actually never more than 3,000. Can you appreciate how different those numbers are? Now, you see a lot of zeros, okay? It doesn't really sink in. So I always think of things in terms of money. Have you ever had $3,000 in your hand? I've had $3,000 in my hand, okay? Have you ever had $150 million in your hand? If you do, I want to be your best friend, okay? I've never. Those numbers are vastly different, aren't they? So we're going from this little chunk of the population to a huge generalization. We're going to be able to say something about the population percentage. Most of the time we'll be right, but some of the time we will be wrong. 2016 presidential election, right? Usually the presidential election predictions are pretty accurate. And they actually got the general vote, the popular vote correct, but the election result they got wrong. So the question is, what causes things to go bad? I mean, why do we get samples that give us bad answers? And that's what we're going to look at today. We're going to start studying what happens when a sample goes bad, what causes a sample to be bad, and what are the consequences of that. Okay? So any questions that we have? Yeah. Mm-hmm. So probability has a very nice applied meaning. Probability in the sense of statistics, one really important application is reliability. So with this method, for example, that we're talking about, what I would really like to know is how reliable is it? What percentage of times does it work? Or in other words, what's the probability that the method is going to give me the right answer? Now, we won't talk about probability the way mathematicians do. So there's like these formal rules of logic and everything. If you want to, take my 412 class. I'll teach you all that stuff. But that's kind of like extra for experts. We don't really need that to do everyday statistics, at least for the type of statistics that we're going to do. So yeah, we will come to that, okay? All right, so let's just do some practice problems. So what we want to do, one of the things we want to do is we want to become comfortable with the idea of population and samples, population parameters, sample statistics. We want to understand the difference, okay? What you're going to find, one of the ways in which statistics is like mathematics, unfortunately, is the fact that statistics is really a bunch of word problems. You're solving real world problems, right? So they're going to be word problems, and you're going to have to translate the word problem into statistics. That's kind of what we did in chapter 2, right? We took a kind of general question and we formulated it into a statistical question. So we have to learn how to speak statistics or something like that. We have to learn how to speak statistics. So here's what we want to do here. We want to go from a statement in words to a statement involving statistical symbols and notation. So the first one says the average cholesterol level of the patients in the study was 108 milligrams per milliliter of blood. So who wants to, and by the way, when I ask you these questions, okay, I know this is all new. You're going to make mistakes. But here, try out your ideas, right? That's how you learn. You try something out, you get it wrong, you figure out why it's wrong, and then you really have it down. So I'll pick on you today, James, right? It's James, right? Yeah, okay. How do you think I should write that?
The average cholesterol level of the patients in the study.
So I want to write this as some sort of statement. I want to use a pi or a pi hat or a mu hat. Which am I going to use here?
Could you use the regular pi?
So here's what I have to know. I have to know what is the variable, right? The way I determine the variable is, the way I determine the parameters, I go back to the variable. So it goes like this, right? Variable, data type, parameter, right? So what is the variable? What is the thing they're interested in this problem?
The cholesterol level.
Cholesterol level, right? And what do you think cholesterol is? Quantitative or categorical? Quantitative for sure. So it's going to be one of these guys. Is it coming from a sample or a population? What do you think? Right, in this study. Okay, obviously, we're not interested in the cholesterol level only in those people, right? We're obviously interested in the whole population. Okay, so we know it's going to be mu hat is equal to 108. Now, typically people do not put units, okay? Statisticians usually do not put units. You can, I won't take off, perfectly fine, but very often you'll just see mu is equal to 108, and you have to go back to the context of the problem to figure out what the units are. Okay, any questions on that? Okay. What about the second one? Logan, what do you think? So same thing, right? Variable, data type, parameter.
So you're studying cholesterol. It wouldn't be with a hat on it because it's of all Americans, right?
Is it? So this is where you have to be really careful. I'm not saying you're wrong, okay? But does anyone have another read on this? Yeah.
Look at American males.
Can you repeat that again, please?
I said you're looking at American males, the whole population of American citizens.
Well, okay, the population's all the things that we're interested in, right? So I can be interested in all American males. And in fact, if I'm going to pose a question, a well-defined question, I might actually want to limit myself. Very often, you'll hear about, American middle-aged males, right? There's a big difference in my cholesterol level and your cholesterol level, I assure you. So that's not really so bad. We can have specifiers on the things, okay? Is there another read on this, though? It says an American male. Does that mean one? Why not? Shaking your head no. There's one word that should tip you off, that it's not just one person. What is that word?
Average.
Average. Again, common sense. Technically, you could take the average of one person. In real life, that's stupid, right? Nobody would do that. So we're obviously talking about not just one. So very often you hear in the newscast, right? The average salary of an American family, okay? We're talking about a population. But here the population is all American males, and we would write it this way, right? Okay, percentage of all voters who would elect a certain candidate is 76%. Let's see, Noah, what do you think? So here's the thing. We have to go back to the variable, right? What is the variable here? What is it that we're getting from the people?
It's not a sample. It would be a population. It's an all voter.
Okay, good. So we're either dealing with a population percentage or a population mean, okay?
But it's a population percent.
Okay, and what makes you think that? What is the variable here?
It says percent.
Okay, you have to be careful though. Because remember, percentage is also a quantitative variable. So I can talk about the percentage of seats in this class that are filled. That's actually considered quantitative. So just because there's a percentage doesn't mean that it's necessarily quantitative. What is the variable here?
It's saying, what do I describe patterns?
Exactly. So the categorical variable is yes or no. We're interested in the percentage, right? Okay, good. Okay, Trump's approval rating from the poll was reported on the news as being 45%. Julia, what do you think? Oh, Julia's not here. Let's see. Niche, what do you think? I'm pronouncing that right?
Yeah.
Okay, good. So just, take your time.
I guess it's only like Trump supporters, Reagan, Sanford, Trump supporters.
Okay, so there's something that's kind of coming out from your responses. So your response earlier was it can't be a population because I'm looking at males, American males. And your response, what I'm hearing you say, correct me if I'm wrong, is that it can't be a population because I'm looking at, you think we're looking at Trump supporters, right? So, okay, so go ahead, kind of flesh that out. What is our population here? We're, all the registered voters, right? One of the things you have to remember is whenever we have a binary categorical variable, we're interested specifically in one of those categories, okay? So I'm interested in the percentage of people that are Christian, the percentage of people that vote for Trump, the percentage of people that are U.S. citizens or whatever, right? So this is going to be a percentage. Is it a sample or a population then? And how do I know? Oops. Eva, what do you think? Sample or population, and how do we know? Anyone want to help? How do we know?
Let's say sample. That's the word poll.
From the poll, right? So polls are obviously samples, right? Is equal to 45%. All right, good. But we all know it's fake news, right? Okay. Okay, so let's go the other way. What if we want to what if we want to translate statement A? Tariq, how would I do that? What would the first one be? Okay, so pi hat. So here's how we think about it. Pi hat, the way we think about it is this is a sample percentage. The hat is right on top. Sample percentage. So this says the sample percentage is 48%, right? Sample percentage of what? We have to be told. We don't know. It's a sample percentage of people who are in the category we're looking for, right? Okay, good. Mu is equal to 125. Sophia, that's who I meant to call before. Sorry. Yeah. So how would I translate that? Okay. Population is 125. Population what? Mean, right? Mu is mean. Okay. All right. Next one, just anybody. Not everyone all at once.
Sample mean is 37.
Exactly. Sample mean is 37. Okay. Last one. Who should I pick on? Carly. What do you think for the last one?
Does it say pi is less than 0.75?
Mm-hmm.
So would it be saying that the population is less than the population?
Population what?
Population mean?
Pi percentage. So it all goes together, right?
Population percentage is less than 0.7.
Right. Or 75%. Okay. All right. Good. So just saying the population is not enough. We have to know population what, right? It's just telling us where that parameter came from. Okay. Good. Yeah. Oh, for A and B?
Yeah.
Okay, so cholesterol level is my variable, right? Let's just kind of take it apart for a second here. Okay, so cholesterol level is my variable. If I can get it to hold still. So that variable is going to be quantitative. So I know I'm going to be working with a mean, right?
You know it's quantitative because it's a certain number?
No, number alone's not enough, right? How do I know that it's quantitative? This is really important. Yes. Excellent. Units. So there's a couple of ways you can do it. The one way you can determine something is quantitative. There are different ways, but there's one way that is most useful, I think. So to determine if it's quantitative, first of all, it has to be a number, but that's not enough, right? You have to be able to do meaningful math with it. So in other words, if I take the average of your cholesterol levels from the last month, that makes sense, right? In fact, we couldn't talk about averages if we couldn't do meaningful math with it, okay? But the most important characteristic, the hallmark, is that it has units. And so you see these units right here, okay? Did that answer your question, though?
Yeah.
Okay, good. Yeah, it's easy to screw up. The way I think about it is categorical. One way to think about it is that the data types actually say what they do. Categorical is values go into classes or categories, right? Quantitative are data, are variables where the values tell you the quantity or the amount of something, right? So here cholesterol level is telling you the amount of cholesterol, okay? The reason why the units are so important is sometimes you're dealing with things like count data, the number of students in the room. That's telling you the amount of students, right? It also has units. One has units of one student. Okay, so different ways to look at things. All right, other questions from that? Everybody's good? Okay. So this is probably, of all the things in statistics that people do wrong, sampling is by far the biggest problem people have. Sampling is incredibly important. So bad samples equal bad data. And what happens when we have bad data? We make bad conclusions. We make bad decisions. So garbage in, garbage out. Okay. We saw that with the Embry-Riddle employees, right? We had bad data that really wasn't representative of Embry-Riddle employees. We came to a conclusion that hopefully is very wrong, right? 80% of the people we concluded were drunk if we didn't know. A really important thing to understand is that nothing can be done to fix bad data. And we're gonna see why. So, best statistician in the whole world cannot do anything with a bad data set. Okay, it's useless. We just have to throw it away. Okay, so the three goals of this chapter, okay, the three things that we really want to understand. First thing is, what makes a sample good? This is a big issue because you never know when you take a sample if your answer is going to be right or wrong. I take a sample for a political poll. I don't know if I'm going to be right or wrong, okay? What we're going to see is we're going to see that if our sample is good, the percentage of times that we're wrong is manageable. I can actually control what percentage of times I'm going to be wrong. Okay, how do we get a good sample? Once we know what a good sample is, how do we get it? How do we go out in the field and actually get a good sample? And the third thing is, what happens statistically when we get a bad sample? Okay. So, what happens statistically? When we get a bad sample. Okay. I'm going to start the roll around, by the way, everyone's here now. All right. So what is a good sample? The key idea here for our first question is that a good sample is said to be representative of the population. Okay? So a good sample is representative of the population. Okay. I apologize for my handwriting. I have to write over the keyboard here. Let me take this off. Maybe it'll make it a little easier. My hand's at a weird position. Okay. So, kind of a cartoon way to illustrate that is mini-me. You guys all seen Poppy Collins, right? Okay. So mini-me is just like Dr. Evil. He's exactly the same, except he's just smaller in size, right? Well, isn't that what we want for our sample? We want it to be the same as the population, just smaller. Now, the big problem is, what does it mean to be representative? What does it mean to look like the population? That's not so obvious question. What do you think that means? Well, we're studying a variable, right? That variable is going to have a certain distribution in the population. In other words, think about registered voters for a minute, right? There's a certain percentage that will vote for a candidate, certain percentage that won't, right? Now there are factors that are going to affect that. What factors affect how you vote? What do you think? What factors affect how you vote? What do you think? You got to be engaged, seriously. You're going to get killed on the quizzes and the activities. What do you think, Ian? You guys are in business. What influences how you make decisions? What factors? Do we all vote the same? Not unless we're in a communist country, right? What's that? Okay, so your political affiliation. What else? Yeah. So we're talking about just like, say, voting for a candidate. What things would affect that? Okay, so location, huge thing in the 2016 election, right? Rural versus city. Yeah, Will. Exactly. So you could say that. You could add to that maybe education, marital status, whether you have children, your age, right? Older voters probably voted for Trump more. Okay, your race, your gender. So all of these factors are going to affect the value of the variable. So what do we want? We want a sample where those factors are kind of in the same proportion that they are in the population. That's hard. Think about it. Just for a second. Think about a simplified model for a voter response. Age, gender, we'll say ethnicity and education. Okay. I got to get a sample that has a balance of all four of those things, right? It has to have the same percentage of educated, say, white voters in the sample as there are in the population, right? That's what we're talking about. All the factors that we think are going to influence our variable have to be roughly in the same proportion as they are in the population. So notice that that word representative, you have to really unpack that. There's a lot of stuff in it, okay? Incredibly hard. What happened with the Trump election? Why did they get it wrong? Well, there were unknown variables. And there were things that they did not think about because Trump is not the usual presidential candidate. So there were new variables. And those were not in the same proportion. We didn't factor those in. So even when you try to get a representative sample, when you're very careful and you try to balance all the factors that you think should be in your sample, there may still be some that you don't know about. Unknown unknowns. So this is not an easy business. So here, for example, if you were just looking at a simplified model where you had a variable that depended upon gender, suppose I wanted to ask, are you for the death penalty? So it's known that men tend to be more in favor of death penalty than women. Okay, I want a sample that has roughly the same percentage of men and women as it does in the population. My variable is not gender here, okay? But gender is a factor that's going to affect my variable. Okay? Okay. Any questions on that? All right. So, how do we get good samples? Okay, so now we know what we want. How do we actually get it? So again, I just want to point out the fact that, getting these good samples is hard. It's hard to get a sample that has the balance of all the factors that are going to affect your variable, okay? So this is kind of what we just did a second ago. But here's how I think about samples and statistics. So again, statistics is just common sense. What do you need? So you're making soup, okay? You're at home making soup, all right? And you want to take a sample. What do you need? First of all, you have to stir the pot, right? If the potatoes are going to go to the bottom, okay? So you have to stir things up, right? To make sure that you have the same chance of getting a potato as a carrot, right? And you need a big enough spoon, okay? If you have a little teaspoon, you're not going to be able to fit all the ingredients on, right? Just like if I have a small sample, I'm not going to be able to get all of those factors in there, right? So those are the two things that affect our sample. So a good sample has to be well stirred. That's what we mean when we say random. In other words, we want to mix everybody up in the population so everyone has the same chance of being chosen. So it's kind of like a well stirred batch of soup. And so what random means in a statistical sense is it essentially means that everyone has the same chance of being chosen, okay? Every individual in the population has the same chance of being chosen. Now, there are a gazillion different ways to sample, okay? And we're going to talk about a few of them, all right? But that's kind of the basic idea. Every individual in the population has the same chance of being chosen. Okay? And of course, sample size kind of means what it says. You want, a large enough spoon. Large enough is kind of relative, but for a categorical variable, usually the sample size has to be at least 100. That's what's considered large enough. And actually, it's generally in the thousands, okay? For a quantitative, we're going to see that we can actually reduce that a little bit. So for quantitative variables, usually the sample size being above 30 is usually sufficient. One of the things that's not so obvious but it's true is that you also don't want to spoon too large, right? So if you say to me, hey, I want to sample your soup, and you give me like a huge container, right? That also doesn't work, okay? Believe it or not, the same is true in statistics. We actually don't want our sample to be too large. Right now, we're not going to worry about that. But we're going to see later on, we don't want to make it too large. Too large actually has a problem too. We can deal with data sets that are too large, but not with the sort of techniques we're going to learn. So we also don't want them to be too large. But for right now, that's not going to be one of our major concerns. Okay, so we want to make sure everyone has the same chance of being chosen. Again, how a statistician thinks about a population, he thinks of them as kind of like a bunch of balls that have numbers on them or something. And he goes in there and, shuffles them all up. And then, so they're well shuffled, everyone has the same chance of being chosen, reaches in and grabs an individual, okay? That's kind of how we think about people in statistics. So we want to go to our last question now. Okay, so we know what a good sample is. A good sample is a sample that's representative of the population. We know what we need to get a good sample. It should be random. In other words, everyone in the population should be stirred up, right? Have the same chance of being chosen. Our samples should be large enough. But one of the questions that's important is, what happens when you don't follow the rules? Why is randomness? And why is sample size important? And those are things that are not so obvious. So now we get to the fun part. But before we do that, anyone have any questions on what we've said so far? Okay, everyone's good? All right. And by the way, I know that some of you see, how many of you see statistics in your other classes? Okay, what class? Which class is that? Okay, interesting. Okay, all right. Other people? Yeah. Okay, all right. Other people? Right. Okay. So if you guys see things, and I know some of you, if you're in aerospace physiology, you could do some genetics and stuff like that. If you have questions, some things you've seen in class, from other classes, feel perfectly free to ask. Okay. All right. So this analogy is actually going to be really important. We're gonna focus a lot on this analogy. And this is a bullseye, a target like you'd shoot at. Okay. The actual bullseye and the target is the parameter. That's the thing we want to hit, right? That's the thing that we want to get. Okay. So this is the bullseye. This is the thing we want to hit. Our shots are statistics. So in other words, I take a sample, I compute a sample mean or a sample proportion, right? And there it is. All right. So the shots are not individuals. The shots are representing statistics that we're getting from samples. So different samples are going to produce different shots, right, on our target. And you think about it, what does it take to be a good shooter? Well, first of all, your gun has to be well sighted, right? That's called accuracy. In other words, accuracy tells you if the center that your shots are centered about is the same as where you should be shooting, right? So accuracy basically is looking at the center, we'll say the location in this case, the location where the shots are centered, and how far that is from the bullseye. All right. So as an example, this would be a situation where you would not be accurate, okay? So I'm trying to hit the bullseye right here, and I have a bunch of shots So this is maybe the sample mean from one sample, another sample, third sample, fourth sample, right? And this is where these shots are centered around. Okay? And so this is measuring the accuracy, how far I am off. This is like a person that's not a bad shot, but they haven't sighted their rifle properly. Okay? So that's what accuracy is. It's often confused with precision. So if accuracy is how well the gun is sighted, what is precision? Well, just thinking about in terms of shooting. It's how good a shot you are, right? If I'm like an assassin, right? You know, heaven forbid. But if I'm an assassin, hopefully I'm really precise, right? I may not hit the bullseye every time, but I'm going to take you out, right? I may not hit exactly the center, but my shot should be really tightly clustered, really close to them, really close together. They may not be close together at the bullseye. I may be a really good shot, but I have a bad sighted gun, right? So this is measuring how spread out the shots are, how tightly they are clustered. So this is not precise. This is very precise. Okay. So this hit may be higher. Right? That you would take it out. Okay. Okay. So this tells us why we need these. Why we need these two things. So here's why we want to. So here's how these two factors play into. So what we want to show now is we want to show how these two things right here, accuracy and precision, are related to the random sampling and the sample size, okay? One of these is going to affect one of those shots, one of those properties of the shots, and the other one's going to affect the other property of the shots. So the first fact here is that random samples produce accurate estimators. Okay, so accuracy is determined by the randomness. So here you can see it in what would be examples of good samples. These are samples whose estimates are centered around the thing I'm trying to hit. Okay? One of the things that makes this picture a little hard to really grasp fully is the fact that we're taking more than one sample. Okay? Again, these are not individual data values. These are either sample means or sample proportions. And there's more than one, so I'm taking multiple samples, right? We don't do that in the real world, do we? If I have a bunch of samples, what do? I glom them all together, right? So this is something that takes a little bit of imagination on your part, because nobody in the real world works with samples of samples. We just put them all together. But this is how we have to think about things statistically if we're going to understand what's going on, okay? So this is an example here of where we're taking samples, and the estimates that we're getting from the samples are centered around some point. This is the blue point here, right? That's off target. And that difference has an actual name statistically. And you guys have probably heard this, people throw around this term, bias. So the difference between what you're trying to hit, the parameter value, and the value that your estimates are centered around, that's called bias, okay? And so what we want to see is we want to understand, why is this true, okay? What's happening here? Okay, so this is a little cartoon to kind of illustrate this. So this represents the state of Virginia, and these are the election results for 2016 presidential election, okay? So as you might imagine, the red areas are where there was support for the Republican candidate. The blue areas are where there was support for the Democratic candidate. And what I want to point out is that it really matters where people took the polls, right? How would you get a random sample? It's actually really hard. And the reason why this is so important is whenever people talk about samples and what goes wrong, almost invariably the first thing out of their mouth is take a bigger sample. But suppose you're sampling in the Southwest. See where that little black circle is? Would taking more people help you? It's just going to give you a more precise estimate of an answer that's really wrong. Okay? So, for example, what happens when we're sampling from these areas here? Well, this is what bias is. Bias in statistics is exactly what it sounds like in regular language. What are you like when you're biased? You're treating one group preferentially over the other, right? Well, what am I doing here? I'm sampling one group more than the other, right? More than they are in the population. So what are my estimates going to look like? Well, they're going to be centered around a value that is not the real value, right? Taking larger samples is going to make this cluster more narrow, but they're still going to be centered around the same value, okay? So this is an example of bias right here. Okay? I'm preferentially sampling Trump. What does it mean to preferentially sample? What am I trying to say here? Okay, Carly, you put your hand near your ears and I call it you. What does that mean? Okay, so in the actual election, I'm trying to remember offhand. I think the actual percentages were, I'm going to make up numbers a little bit. I think it was 48% for Hillary, and I think it was something like 46% for Trump. Okay, that's the percentage in the whole population. So this is pi, right? All right. So what's going wrong when I'm sampling the red areas? What do you think now? And what I'm actually doing, to put a finer point on it, is I'm actually oversampling the subpopulation, aren't I? Trump supporters are only 46% of the whole state, but in those red areas, I forget what it is, I think it's like 70% Trump. So when I take samples from there, I'm basically oversampling one of the subpopulations, right? I'm taking samples from. Okay, let me put it this way. I'm taking samples from a region that's not representative of the population, right? That's what's going to cause the bias. So these estimates are going to be too low. What happens when I oversample from the blue areas? Again, I'm sampling from a population, a region that's not like the actual population, right? So I know my estimates are going to be higher. They're going to be centered around a value that's higher than the actual value. So these are biased against Hillary. These are biased for Hillary. What would this be? This would be a sample if I did maybe a random digit dialing, right? It might be hard to figure out how do I choose. Do you see how hard sampling is? You have to kind of choose things in such a way that you're basically not oversampling any one area. Maybe random digit dialing. I could know all the area codes and screen it, right? And randomly call numbers. So you have to think about it. It's not so obvious, right? But this is what bias is. This is why randomness is so important, okay? Notice that I didn't mix everyone up. Not everyone had the same chance of being chosen, right? These Hillary voters over here, these Hillary supporters, did not have a chance of being chosen because I limited myself to here. That's why randomness is important. Everyone has the same chance of being chosen. Because when everyone has the same chance of being chosen, we're more likely to get samples that look like this. Okay? Where we're getting the correct proportions. Okay. So randomness determines accuracy, which means what? Precision must be determined by what? Sample size. Okay? And this is something that almost everyone in this room probably knew when you were in 5th grade, right? If you want a better estimate, you take a larger sample, right? And as long as your sample is random, you're going to get a really good answer. So this is an example of estimates that came from larger samples. These are examples of estimates that have smaller samples, okay? Why do they spread out more? Well, smaller samples are more affected by extreme values, right? Whereas when you have larger samples, the values tend to balance out more. They tend to be more like the value in the center, okay? So it's kind of, again, like that small spoon analogy. Small spoon, I might get carrots and a few sprigs of parsley, right? You know, bigger spoon, I can get, you know, more of the ingredients on there, okay? Let me show you one last thing, okay? Kind of tie together the theory part, and then we'll start on computations, but I want to show this to you. So this is a chapter 3 overview. Okay, so to kind of put everything in perspective, okay? Chapter 2, we said, okay, we start with a question. We have a statistical question. It's a question about the population parameter, right? Everything seemed fine and rosy, but then we said, oh wait, we can't get the population parameter. So now we have to take a sample, okay? So this is where we're at right here. So what are the main principles here that we want to take away from this? Okay. First is that samples estimate populations. That's the whole point for the sample, right? I want to compute something from the sample that's going to estimate the thing that I want and I can't get, okay? So this is the basic idea. Okay, so samples estimate populations. What do we need to get good estimates? We need good samples, okay? So we're looking for an estimate. We want our estimate to be good. We don't want to be like that mechanic that says the brake job's 350 and it's 780, right? So the way we get these good estimates is we have good samples, okay? And the general principle is that the sample is representative of the population, okay? Okay, so how do we get good samples? We have good samples when our sample is random and it's large enough. Why is random important? Because random is going to affect the accuracy of our estimates, and the sample size is going to affect the precision of the estimates. We're not going to prove any of this, but you can mathematically. If you take 412, we actually prove these things. But they're kind of like common sense, really. I mean, if you go back to that election example with Clinton, it kind of makes sense, right? That estimates taken from a red area should be centered around a value that's much lower, right, than the general population, because you're oversampling a certain subpopulation, okay? And again, sample sizes affecting precision, that's something that's pretty intuitive to everyone. I've never had anyone say, I don't get that. It just makes sense. If you want a better estimate, a more precise estimate, you have to take a larger sample, okay? And that's pretty much all there is to know as far as the principles. So what we'll do next class, we'll talk about, well, how do we actually do this on the computer? This is all great in theory. So we're going to talk about how we actually do this on the computer. We'll do some practice problems to help prepare you for the homework, and we'll have the quiz, okay? And I'll post the practice quizzes by Friday, so you can come by in office hours, or you can see Greg, okay, during the SI. And I'll post the video today. All right, thanks a lot.